Well, here we are in a new lecture theatre. So, there are two ways of looking at this. The one in your notes is the one I'm about to write. If a series converges, then the limit as n goes to infinity of an has to be 0. This is easier to write and makes a lot of sense. And this one is how you would use it if you wanted to show that something didn't converge. The big point is that if the limit of the individual bits does go to 0, it tells you nothing about whether the series converges or not. So it's important to realise that this only tells you that things doesn't converge. It never proves that things do. So I just need to do an example of this in use. This, for example, the sum of this, I might even make it a bit more spectacular. So when n is 1, I get minus 3 over 49, and then I add on what I get when n is 2, where I get 1 on whatever I get. 1 on 12, 13 square, 169. And when n is 4, I'll get something else. So I will continue to get different numbers and I'll add them on. And the first several are quite small numbers. But the thing is, the question is, if they don't remain small, and they have to not just be small numbers, but get smaller and smaller and smaller if it's going to converge when I add them all together. So I just want to be sure of this. This one, when n is 1, what did I get? Minus 2 on 49. 2. Uh, 6 on 18, 19 squared. I don't know what 19 squared is. And so on. That's what it is. I don't need to write that down to understand this series. That's bad. We need better lighting. Meh. Okay. To understand this series, but I just wanted to point out that they're all quite small numbers. But I need to know if to converge, the limit of that bit would have to be 0. And so that's what I'm going to do. So I would need to do the limit of that thing as n goes to infinity. Yeah, of course. I would need to do the limit of that thing as n goes to infinity. Now, technically, n is only a whole number, and so in complete technical, if I'm being completely technical, I can't differentiate those things because they don't exist when n is something other than a whole number. So I'm technically not allowed to use L'Hopital's rule. I can, it still comes to the same answer, but I won't. So when you have something, as the thing goes to infinity, the safest thing to do is to divide the top and bottom by the biggest power of n that you see. So on the top, I've got an n squared, and on the bottom, if I expanded that out, I get an n squared as well. So if I divide the top and bottom by n squared, then I should be able to figure out what the limit is. The nice thing about squares is that they expand out over division and factorise over division. So this is the same as 6n plus 1 over n squared. And most people would skip that line of working that I just wrote. But if you're afraid of getting it wrong like I am, then you'll do it. So 6n divided by n is 6. And so I get this. And as n goes to infinity, this bit is 0 and this bit is 0. Which is a very small number, but isn't 0. So since the individual pieces don't go to 0, this diverges. The reason this works is that as small as these numbers are, eventually when I go far enough, it's just the same as adding 1 on 36 plus another 1 on 36 plus another 1 on 36 plus another 1 on 36 forever. And if I add enough of them, I can get as big a number as I want. There you go. In past exams, there's been a classic exam question that had one of these, where you just had to do the limit and go, diverges. Did you have something to say? No? I thought you did. So you should always check that, even if you just quickly do a little scribble that wasn't proper working on the side, to check before you do anything else. Right. So it is because this isn't equal to 0 that I know that it diverges. Okay. All right. So the next test that I know of, can I just check something? Do they still have the alternating series test? Oh, that's sad. Oh well. Is in the notes? Sorry? All right.
We can go through it anyway.
I just don't want to give you something that you think you expected to know. But if it was mentioned at any time in the course, the lecturer says that's fair game. Yeah. Okay, so I'll just mention it. You know how I said that if this does come out to 0, then you don't know if it converges? Well, if it does come out to 0 and it's an alternating series, then yes, it does. That's basically it. But I might just leave that for the moment and go straight on to the ratio test. Okay. The ratio test is a way of telling whether a series converges by comparing it to the way a geometric series behaves. So in a geometric series, if that thing in the brackets with the power is less than 1, then the series will converge. And a geometric series has the property that each term that you add in your running total, each extra bit that you add, is the same multiple of the bit before. So when I did my 1 plus a half plus a quarter plus an eighth, the bit I add is half the size of the bit I added before. And so I do this ratio between the successive terms, and if it comes out to less than 1, then basically my series is in a way smaller than the matching geometric series. That's the idea. I'm comparing it to the way a geometric series works. So here's how it goes. So part 1 is I have to find the limit of this thing. So I'm going to calculate this. Just a second. I think that's right. Each one divided by the one before it. Yes. So it could be n plus 1 on the top and n on the bottom, or it could be n on the top and n minus 1 on the bottom. It doesn't really matter. This is the traditional one, I think, in the lecture notes. So you calculate that, and then once you've got that, you find the limit of that as n goes to infinity. All right? And if that limit, I shall call it r, because it's a ratio. If that r is less than 1, then it converges. If the r is greater than 1, then it diverges. And if the r is equal to 1, sucks to be you, it doesn't tell me anything. Then it tells me no information whatsoever, and it's been a waste of everybody's time. So the situations in which this r will come out to be equal to 1 tend to be the situations when you should have done this that I did before. So that's why you should always do this first, just in case. Yep, if the limit's not 0 in that first test, it diverges, you can stop. And the sum doesn't mean anything at all. Okay, that's the ratio test. It's complicated, but essentially I'm comparing my series to a geometric series. Note that neither of these tests tell you what it actually converges to, it just tells you whether it converges at all. This one's fun. Okay. I know what this converges to. Well, at least if it started at 0, let's do that. I know this converges already. That's e to the power of 2. Because that's what I get when I put x to the power of n over n factorial and I put x equals 2. This is e to the power of 2. I know this converges. So I don't have to actually do this. I can just say, oh, well, that's just the Taylor series for e to the x when x is 2. Bang! Converges. But I'm not going to do that because I want to illustrate the point. So let's just make it harder. Yeah. Okay. Oh, fun. That's like, oh, it's like E. I don't know. Still converges. Okay. So I know in advance this is going to converge because I happen to know about these things. So n factorial is super duper. If it's on the bottom, in general, everything converges. So it's usually a good sign. So here we go. So an plus 1 is 2 to the n plus 1, n plus 1 plus 3 over n plus 1 factorial. That's what an plus 1 is. I put n plus 1 everywhere there's an n. So an plus 1 over an. Oh, crap, just a second. Yeah, we need some absolute value signs. I think technically the ratio test is only defined for things that are already positive, but if the positive version converges, then so does the negative, so does the alternating one, so it doesn't matter. So we'll get 2 to the n plus 1, n plus 4 over n plus 1 factorial divided by an, which is the same as multiplying by 1 over an. So I pulled a little Swifty there. Yep.
So your R is going to come out to an absolute value. So that means when you remove the absolute value, it's going to be between two values, like if it converges.
Yep. You're getting ahead of yourself. Yes, we were going to do that in a minute. Okay. So that's that. But all of my numbers were positive anyway, so it doesn't really matter. So, yeah, if I wanted to make it really fun, I would put like a -2 inside the power of n. That's fun, let's do that. So every so often in revision seminars I say, wouldn't it be fun if you could change the exam question while you were doing it? But this would be like really fun because you'd be basically saying to the examiner, your question isn't hard enough, I'm going to change it to this. Okay. All right. So here we go. We're going to have to deal with 3 different kinds of things here. We have powers, we have factorials, and we have polynomials. So I'll deal with each of them separately. So -2 to the power of n plus 1 divided by -2 to the n. When you divide powers, you subtract the powers. Divide exponents, you subtract the powers. And so I'll have the n plus 1 minus the n, which will leave me with just a -2. Okay. So that's these things. N plus 1 factorial and n. Interesting, n factorial. Well, n factorial is 1 times, I'm just going to write it out. That's what n factorial is. And n plus 1 factorial goes up to the next number. And all this bit cancels. Yay! And now it's probably time to deal with that absolute value. Well, the absolute value of -2 is just 2. And these are all positive numbers anyway, because n is going to infinity, right? So now I need to do the limit of that as n goes to infinity. The reason I don't do it from the beginning is because I don't want to keep writing lim n goes to infinity on every line. Stupid. Could waste precious seconds in an exam. Oh, look, it's another n goes to infinity. I should divide by the biggest power of n that I see. It's an n squared on the bottom, and that means I should divide the top and bottom by that would be a 1 on n. That would be a 4 on n squared. If I divide this one by n, I'll get 1 on n. And then this one I'll get 1 on 3 on n, like that. So I divided the top and the bottom by n squared to get from there to there. So dividing by n squared is the same as dividing this one by n and that one by n. Which is 2 times 0 plus 0 over 1 plus 0 times 1 plus 0, which is 0. Yay! Now let's see. We look at this answer and we decide whether it's more or less than 1, and 0 is less than 1. So it converges. Yay! Okay. You will have the tendency that if there's factorials on the bottom, it'll come out to 0 when you do your ratio test. It's extremely common for people under stress to look at that answer of 0 and say, there is no conclusion. Because in most people's minds, 0 means nothing. And so they go, oh, 0, that doesn't mean anything. And so there's no conclusion. But it's a proper number and it's a number less than 1. And so it converges. That's just human psychology and the number 0. Okay. It is possible for it to come out to something other than that. It could come out to something bigger. It could come out to other things. And that would be okay. Yes?
Why do we divide by n squared if I don't see any n squared?
There is an n squared, because if I multiplied this out, it would come to an n squared at the front. That's why I divided by n squared. The other way of doing it is say, well, if I divide this one by n and this one by n, that's the same as dividing the top one by n twice. Because the point is I actually just want to write everything in terms of 1 over n's. Because 1 over n is and 1 over n squared and whatever are the only limits I actually really know at infinity. A really good point, actually. Okay, so that's pretty much all the tests that we have. But I do want to do an example where we don't know in advance what, well, I know what it's going to be. So I'm just going to do another example. This isn't relevant to this question, but did you do anything where you like differentiated power series to figure out new ones? Okay. All right. Here is a thing, and I would like to know whether it converges or not. So I could do the ratio test. And the ratio test will definitely tell me whether it converges or not. But I have another plan. This has got a lot of, they're all powers, and I know a sequence that's got powers in it. It's a geometric sequence. So if everything is powers, it should be possible to turn it into a geometric sequence, geometric series. And that's what I'm going to do. I'm going to turn this into a geometric series. So if I can rewrite this as thing to the power of n, then I'll be able to use the facts about geometric series to tell me whether it converges or not. Well, 2 to the power of 2n would be the same as 2 to the power of 2 to the power of n. And 5 to the power of n plus 2 would be the same as 5 to the n times 5 squared. So what I've done is I have looked at what I've got there and said, ooh, I would really like to write it as single thing to the power of n. And in this one I can do that by doing powers of powers, and this one I can do by splitting the plus like that. Just done some moving around. That 5 squared on the bottom, I'm just pulling it out as a 1 over 25. And the 2 squared to the n is 4 to the n. So the 1 over 25 doesn't have an n in it, so I can pull it all the way out the front of the sum. And the 4 over 5, well, powers distribute over division, and so I can pull that out as well. And now, this bit is a geometric series, and therefore converges because the thing inside the brackets is less than 1. Yay! I can even figure out what it converges to. So I can say at this point, geometric series 4/5 is less than 1 converges. Since it's a geometric series and that number is less than 1. But I can even figure out what it converges to. Okay, so if it started at 0, I could use the formula, but it doesn't start at 0, so I'm going to have to figure out what to do instead. Well, I have some ideas. What ideas have people got? What was that?
Start from 0 and subtract whatever's left.
So start from 0 and take off the first few.
Yeah.
That's a good idea. So that's one option, and it's a perfectly good option, and it will definitely work. But I'm not going to do it, because I have something that's even more fun. But like, that's a perfectly good thing, and it would totally get you an answer. I'm in fact going to do both of them. So way 1. would be 1 over 25. And we'd have the bit starting from 0, but we don't want the bit where n is 0, and we don't want the bit where n is 1, and we don't want the bit where n is 2, but we want everything after that. So we took those parts off. Oh, nope. Minus 1, minus 4/5, minus 16/25, which is whatever it is. Right? All right, so that's one way. Way 2. There's another way of doing it too. I can see some people discussing, so I'm wanting to know what their ideas are. Yeah? Ah, so from 0 to infinity and take off 0 to 3. Cool. So you're thinking something like this. Oh, that's this again, really. Okay, yep.
Could you set the start of the sum to n equals 0 and then change the expression to n plus 3?
Ah, so we start the thing at 0 and change the thing to n plus 3. That's an option 2. So yours would have been really, really good if it had started like 57 or something. And you could have the sum, as long as you knew how to add up a sequence, like a series to a running total. Do you guys have that formula too? Okay, might need to know that. Okay, and your idea is this, just let me see if I've got this right. You're saying that I really want this to start at 0, and that would be the same as doing this.
Yes.
Yes? Well, let's just check. When n is 3, this comes out to 4/5 cubed. And when n is 0, this comes out to 4/5 to the power of 3. Yep, when n is 4, this is 4/5 to the power of 4. When n is 1, this is 4/5 to the power of 4. Okay, every number here gives the same answer as the first number here gives the same answer as the first number here, the second number here gives the same answer as the second number here, and so on forever. So these two are actually the same sum. So if you want a rule that's a slick trick, if you take 3 from here, you need to add 3 here. And infinity minus 3 is still infinity. So, okay. And this is cool because adding up in the powers is multiplication down here. So I can take this out. Whoops, sorry. So I can bring the cube out the front, and then this thing I can use my magical formula 1 over 1 minus x. So they're both perfectly good possibilities. I don't know if this was an exam, if they would want you to finally simplify that answer to an actual number. But this one's probably easier to simplify than that one. I do want to show you a magic trick. The magic trick is how to simplify this without actually doing flipping fractions. I just think it's fun. That's not a 3, that's a 3. So I don't want that to be a fraction within a fraction. Nobody likes fractions within fractions. So I really don't want a 5 on the bottom of that. If I multiplied the bottom of this by 5, then it wouldn't be there. And being a fraction, I can times the top by 5 as well. So I'll times that by 5, and times these by 5, and I get that. Yay! Magic trick. Which is conveniently 1. I'm not going to finish it off from there. I just thought you'd like to see that. I think it's fun. Okay. Right. So the only other thing I can think of to say about series would be to talk about power series, which I think is in your course too. Because I seem to remember someone writing on the blackboard in the other lecture theatre, interval of convergence. So I might talk about that. Okay. So we've been doing very well, and we've looked at a few specific series that have specific formulas for what the different terms are. And some of them have worked no matter what the number is. So back here at the beginning, we had this one here, that no matter what x is, well maybe not no matter what x is, but for some x's it comes out to a specific answer, and for other x's it doesn't converge. And so what we have here in a way is a formula that takes x and produces a series. And that's kind of interesting. And in fact, in some ways it takes x and sometimes it produces a number, and sometimes it produces the statement, this series diverges. So that's what we're going to talk about next. In a way, they're sort of functions from x to the set of possible series. And that's what a power series is. So we've seen a power series already. We've seen two of them actually. We've seen this one, and we've seen, oh, that's in the wrong spot. And this one. This one up here doesn't count as a power series because it has to be number to the power of n. This is n to the power of number up here. This one is, because it's x to the power of n, it's unknown number to the power of n. This one is n to the power of unknown number. That's a whole different thing. That's not a power series. That's a p series. Okay. So a power series is something like this. It's some function times x to the power of n. A lot of people will put an a in that spot, but in my head, an is all of this. And so I don't like to put an an there. That's, all of that is an. Maybe I can... Oh. Ah, well. Nope. All right. Sorry. Oh, that's slightly better. Okay. So that's what a power series is. And the point is, different x's give different series, and different x's give different answers to whether it converges. So they give different answers, they give different series, slightly, and different x's give different answers to does it converge. So if it does converge, then technically this is a function. It takes x, it produces a series, and we add it up, and whatever number that is, that's the answer for the function. But if it doesn't converge, it's not really anything. It just takes x and produces this symbol that doesn't mean anything really. It's not a proper number at all. In some mathematics, they take the ones that don't converge and give them new meanings and run with that and see what happens. Yeah, that's weird-ass stuff. But today we're not going to go there. We're going to think about this one. And the in particular thing we are most interested in is this question here. Which x's make it converge and which ones make it diverge? And the answer to which x's make it converge, the answer to that question is the interval of convergence. Every x in the interval of convergence makes the series converge if you replace x with that number, and every number outside the interval of convergence, if you place x with that number, it doesn't converge. So it's almost as if we have this new kind of function which says these are the possible x's, and here we have converge and diverge, and we just put a dot where it converges and where it doesn't. So there will be somewhere in the middle so these x's it diverges, suddenly at some point there will be an x where it starts to converge, and these x's will converge and suddenly, and then at some point later there will be some x's where it diverges again. That's what it will look like. And I need to adjust something I wrote earlier, I'm sorry. It might not be x to the n, it might be x minus something all to the power of n. So the first thing to know about this interval of convergence is that right in the middle, that's the number c that I wrote above. So if it's x minus c, then right in the centre of the interval of convergence, that is guaranteed to converge. Because if x was equal to c, then this would be 0, and we would just have a list of zeros. And if we go from the centre to the edge, there's a name for that in geometry. It's called the radius. So going from the centre to the edge, that's the radius, and it's called the radius of convergence. So what we want to do is figure out what this zone is. Now, some decent mathematical theory tells us that if you have the collection of x's which make it converge, it must be an interval. Now, there's no reason to expect that. It could have been some random collection. There's some over here and some over here and some over there. But actually, it has to be an interval. It's possible that the interval goes on forever and it converges for everything. It's possible that the only number in that interval is 0 and it only converges at one point. But mostly it tends to be a little nice, neat interval. And it could be closed at both ends. It could be open at both ends. It could be closed at one end and open at the other. They're all possibilities. So, how are we going to tell whether it converges or not? And this is where the ratio test comes to the rescue. Where the ratio test allows us to figure out when it converges, because we can figure out what that ratio test would give as a formula based on x. And then we can say, well, if the x makes that thing come out to be less than 1, then it converges. If the x makes that thing come out to more than 1, then it diverges. There we go. So let's see. Probably easier to do with an example. I don't know. Yeah, let's do that. I have no idea what's going to happen, so I'm just going to give it a go. So this is my power series. It's got random crap here next to the x minus 3 to the n. Okay, let's do our ratio test. So I'm putting n plus 1 into the formula instead of n. And then I'll divide by an. Oh, that's too hard for me to do in my head. I'm just going to... Okay. And... all right. So you'll notice that I didn't do it as the upside down thing first up because, I don't always do it the same way. I'm always making stuff up on the spot. Yeah. Something like that. The thing on the bottom of the top will end up down the bottom, and the thing on the bottom of the bottom will end up at the top. Yes, okay. Right. Alternatively, and this is fun, you could multiply this by 2 to the power of n plus 1 and this. That'd be fun too. Anyway. So most of that 2 to the n cancels with this 2 to the n plus 1, and we end up with a 2 on the bottom. This top's not going to be fun, so I'll just leave that there. And the x minus 3 to the n plus 1, most of that cancels with the x minus 3. And so I just end up with that. So the n plus 1 divided by the thing to the n, we subtract the powers and we just end up with a 1. Okay. So we want the limit as n goes to infinity of the absolute value of an plus 1 over an, which is the limit as n goes to infinity of... well, when we do the absolute value of this, that's a positive number anyway. And that's a positive number anyway. And so they won't matter when I do the absolute value. And I'll get the absolute value of x minus 3. Cool. So this x minus 3 doesn't have an n in it. So I can actually bring that out the front. And let's be a bit dangerous and figure out what happens when we divide our top and bottom by the things as they go to infinity. So divide this one by n squared. On n squared. Divide this one by n squared, I'll get a 1 on n squared there. And this divided by n squared would be the same as dividing this by n. Probably would have been quicker to expand it out, but anyway. Alright. So we've got 1 plus 0 squared plus 0 over 2 times 1 plus 0. So I've got, sadly on the next page, if I'm very clever, times 1 over 2. Sweet. Doing well. So this is what I get when I do the ratio test. And different x's give me different answers. So some x's, this number will be less than 1 and it'll converge. And some x's, this number will be more than 1 and it won't converge. And some x's, it'll be equal to 1 and I won't know anything. And so in order to converge, we need this number that we just calculated times a half to be less than 1. Which means I need x minus 3 to be less than 2. Just multiply both sides by 2. And this number here, when I get it to this stage, where it's just x minus something, there's not allowed to be a 2x minus something, you're going to have to deal with that if it's there. X minus something, absolute value less than number, that number is the radius of convergence. Well, we can go a little further than this. If x minus 3, the absolute value of x minus 3 is less than 2, that means that whatever number x minus 3 is, it has to be between minus 2 and plus 2. And now if I add 3 to all of these numbers, I get that. And let's just check that the radius is working out. The distance between the bottom end and the top end is 4, and the radius should be half of that, which is 2. Yes, it's all working. Okay, I haven't done any of my maths wrong in between there and here. And you should also notice that if I draw it on a diagram, here's 3 in the middle, and this says that the distance between x and 3 has to be less than 2. This is 2 up, which is 5. This is 2 down, which is 1, and it's between here and here. Okay, that's what my interval of convergence looks like, but I'm not quite finished yet because I don't know whether I should be colouring in these endpoints or not. So I'm going to have to check those separately because the ratio test won't work at those ends, because when x is equal to 1, this answer here comes out to exactly equal to 1, because I get absolute value minus 2 times a half, which is 1, and that's not going to help. So I'm going to have to check the ends. When x is equal to 1, x minus 3 equals negative 2, and my series becomes that. Because when you do powers, the powers can spread across division. So minus 2 to the n over 2 to the n is the same as minus 2 divided by 2 to the n. And that, the individual terms don't go to 0. The limit as n goes to infinity of n squared plus 1 minus 1 to the n is not 0. In fact, that limit doesn't even exist. It alternates between plus very large and minus very large. So it diverges here. And when x is equal to 5, x minus 3 is equal to 2, and we get n equals 0 to infinity n squared plus 1 over 2 to the n, 2 to the n, which is just n equals 0 to infinity n squared plus 1, and the limit as n goes to infinity of n squared plus 1 is also not 0, because it's infinity. So this diverges too. And so therefore the interval of convergence doesn't include 1 and it doesn't include 5. Is from 1 to 5. If I had found that it converged at one of the ends, I would have put a square bracket here to say it's included. Yay! You will have the tendency that if there's a polynomial bit like this and a power bit, then the power bit is what will provide the number for the radius of convergence. Now we got a 2 here in our radius of convergence, and that came from this 2 to the power of n on the bottom. If the 2 had been on the top, then the radius of convergence would have come out to a half. So it's nice to explicitly try to develop instincts for what you think ought to happen, so that when you're in an exam you can go, oh, that feels funny, and you can check your work. Right. So I should just say a little bit of one what if that's off the top of my head. What if, when you did this, you got 0 times x minus 3. Which would be 0 no matter what x is. So then what that means is you're saying, well, to converge, we need whatever this answer is to be less than 0, less than 1, and 0 is less than 1 no matter what x is. So always true for all x, and therefore the interval of convergence is every real number. Just so you know what might happen. So this is the one time when you got less working. If you've got some factorials on the bottom, this will generally happen. You will get to, if you get to 0, regardless of any x, then it always converges, and the interval of convergence is the entire real line. And you can just stop. All right. Any thoughts or questions or comments? Actually, please ask me a question. Yep. We don't need to check the endpoints because it doesn't have endpoints. It goes forever. Because the radius is going to be 1 over this number, which is infinity. Yes? Okay, could people please just shh, please? What was that? So the radius of convergence is just this number. It's how far the edges of are from the centre. The interval of convergence is the description of this entire little region here.
So the radius is half.
The radius is half of the width of the interval. So if someone gave you an interval of convergence and said, what's the radius? You just find out how wide it is and divide by 2. All right. Yeah. How did I do this? Yeah. This may or may not help. Guys, it's really, I can hear a lot more than you can there. It tends to collect this way, so you might just more whispery. Okay, so you're thinking that when you see, that's not going to help. Okay, the general rule for fractions, it can feel more complicated than this, like that, is that when you divide fractions, it comes to the same answer as multiplying the opposite of the bottom. This one here is upside down here. And as long as you... So I did a bit of a Swifty there where I went, well, the bottom of the bottom ended up on the top. And the top of the bottom ended up on the bottom. So if it's on the bottom twice, it ends up on the top. But that doesn't always help everybody. So when I did it earlier with this one, this one's a bit more complicated because there are some things that are fractions and some things that aren't. But I can see this as a fraction here and a fraction here. So this is this times that divided by this times that. So No, I need more space than that. So anything that's on the top will stay exactly the same as it is. Fractions on the bottom will end up the other way and multiplied instead. Like that. And things that are on the bottom will still be on the bottom afterwards. Technically that, because this is the same as this. Like that. Yeah. When you've got fractions and things that aren't fractions, it turns to crap. But if you multiply fraction by a number, it can just be subsumed into the top of the fraction. Yeah. Okay. Now, I said I would finish at 3, but I will keep talking until the recording stops. So if you're happy to stay, then, you know, I can talk about something else. If you want to go, I will not be offended. So, what might people want? Yes? Oh, binomial series. Okay, sure. So I suppose the binomial series technically goes back in my classic series, but it is a power series, so I'll just run with what I've got. The binomial series is my favourite series because of the hard yards that I did trying to figure out what the hell was going on. Okay. Now, if it's what I think it is, I might need to look at the notes, but if it's what I think it is, then it's this. No, damn it, we've already got an N. Let's call this an M. This is the binomial series. 1 plus x to the power of m, the top number, is the sum of these things. So just to be clear on this, when n equals 0, it will always be 1. And when n equals 1, we'll get m choose 1x. And when n equals 2, we'll get n choose 2x squared, and so on forever. Now, I may need someone's notes to check if this is what your notes say. Sorry? Okay. Now, this is lovely. But the fun thing is that we can do it even when m isn't a whole number, even when it's negative. Yay! Okay. So, right. So this is pronounced m choose n. Only that's what it is when m and n are both whole numbers and n is less than m. Okay? So, if you don't want, it's not really about choosing if you don't have the right numbers. But if your numbers are the right numbers, it will be the number of ways to choose n things out of m when that makes sense. So whenever that makes sense, it's the number of ways to choose n things out of m. But if that doesn't make sense, then it's not that, because it doesn't make sense. So, just as an example, 12 choose 3 is the number of ways 3 things out of 12. For example, the number of ways to choose 3 months out of the 12 months. So I could have January and December and March and April and September and March and all those different possible choices of 3 months, not in any particular order, out of the 12 months. That's how many there are. Yep?
But like order and repetition matter as well.
No.
No?
Not for this one. Order does not matter.
And you can repeat as well.
No. No repetition, but order doesn't matter. Okay. Right, but the key is not what it means. The key is how we calculate it. So you may have been taught to calculate this in a certain way using factorials. Don't. That's not how we're going to calculate it. We're going to calculate it this way. So on the bottom we will have 3 factorial. That doesn't change. And on the top we will have the same number of numbers as we put there, but starting at 12. Like that. So on the bottom we had 3, and that became 3 times 2 times 1, that's 3 factorial. And on the top, well, there were 3 numbers on the bottom, so I will put 3 numbers on the top, and I will start at 12 and work my way down. And that's the answer. That's what I get. Which is whatever it is. It's like 220 or something. I don't care what it is. Okay. Okay, just as another example so you can see how this works. 7 choose 5 would have on the bottom 5 factorial. And on the top it would start at 7 and work its way down until we had the same number of numbers on the top as there were on the bottom. That's how we calculate choose. Cool. Now for some numbers that we could put in there, it doesn't make any sense that it is the number of ways to do that. But we're still going to calculate it anyway. Watch this. Oh, there's no line there. 12.7 choose 3. Now, it doesn't make any sense whatsoever to choose 3 things out of 12.7. But that's fine. We're just extending the calculation, not the meaning. So we will have on the bottom 3 factorial. And on the top we will have 12.7 and 11.7 and 10.7. We will start at that number and go down by 1 the same number of times that 3 factorial went down by 1. This doesn't...
Why would you choose the highest rate out of 5 or whatever?
Sorry?
Why don't you choose the highest 5? Like you can say choose your number.
That's how it's done. It's the highest 5. There is a reason. There are 2 reasons. One is that when you do choose, technically you actually do 7 factorial and you remove the lowest ones because they're the ways to rearrange. Well, when you're doing choosing, there's 7 ways to choose the first one, and then since you've already chosen one, there's 6 ways to choose the next one, and since you've already chosen 2 of them, there's 5 ways to choose the next one. And so the number keeps going down because every time you choose one, there's less to choose from. That's why it goes, there's the top several. And when you're doing this one, well, we're just copying the same pattern. So that's just what we're doing. So what's this? Minus 5 choose 3. So that would be 3 times 2 times 1, minus 5, minus 6, minus 7, because I subtract 1 each time. So I start with the top number. So I have 3 times 2 times 1. I'm going to start with minus 5, and I'm going to have 3 of them going down. Okay, this is fun. So, therefore, 1 plus x to the half, according to this, will be 1. The first one's always 1. And we will have a half choose 1 times x plus a half choose 2 times x squared, plus a half, choose 3 times x cubed, plus forever. One. Now, anything choose 1 is always the same number because you just have the number 1 on the top and the number that you had on 1 on the bottom and the number 1 on the top. So that'll be a half of x. This will be 2 times 1 on the bottom and a half times, well, when we go down 1, we get to minus a half. And this one will be 3 times 2 times 1 on the bottom, and we'll have a half and minus a half, and we'll go down another 1 to minus 3 on 2. And so we have 1 plus a half of x plus, note this would be a minus by now, so minus an eighth of x squared, and we've got and 2 minuses, so it'll be a plus. Oh wow, okay. The 3 on the top will divide by 3 on the bottom, they'll cancel. 1 on 16 x cubed. This pattern doesn't actually continue. I mean, we jumped by 4 here and only 2 there, so weird crap is going to happen. Yeah. So this is what 1 plus x to the half is, as long as the size of x is less than 1. So for numbers close to 1, 1 and a half to the power of a half will be equal to this if I put x equals to a half in there. And that'll be great. There you go. There is nothing more special, pardon me, to it than that. It allows me to straight up write the Taylor series of something without having to do any more work. The reason this works is that when you do a Taylor series, you'll do derivatives of things, and every time you do the derivative of a high power, you keep multiplying by the current power. So if I started with something to the 6, then the first derivative would be 6a x to the 5, and the next derivative would be 6 times 5a x to the 4, and the next derivative would be 6 times 5 times 4a x cubed, and so on. And if I went all the way down to the bottom, I would end up with 6 factorial times a. Which is really cool. So I differentiate something often enough, I'll get down to a constant which will be something factorial times whatever I started with as my coefficient. And so this should be the constant term of whatever I started with. So if I had other crap here, the constant term is this. And so the constant term when I differentiate 6 times will be 6 factorial times whatever that coefficient is. And so if I differentiate enough times, find the constant term and divide by 6 factorial, it should tell me what that number is. Which is why we end up dividing by 3 factorial or 4 factorial or whatever it is when we do the binomial theorem. That's not a very good explanation, and I can do a better one if you want me to. It's just that everything is connected to everything else with this stuff. Yeah. So I don't know if there are any particular examples of the binomial series in use that are confusing to anyone. I know one. It goes, find an approximation to like root 26. Using the binomial theorem. And so I could go, oh sweet, this root 26 would be the square root of 25 plus 1, which is great, right? Because the binomial series is like 1 plus x to the half, except it doesn't work if the number you have here is more than 1. Which is sad, because that's way more than 1. So, okay. Just a second. What if I did this? And pulled out a 25. Because then 25 to the half is 5. And this to the half is still a half, and that number is less than 1, so I can use the binomial series. 1 plus a half of x minus an eighth of x squared plus a 16th of x cubed. That's probably far enough. And that I could calculate. Probably only need to even go this far to get something pretty good. Because, 1 over 25 cubed is pretty small. Oh wow, what is that? 25 squared is 5 to the 4. Yeah, I'm only going to go this far. Yeah. Yay. So 5.1 minus 0.00. There we go. Pretty sure that's what the answer is. That's definitely that's a tenth. That's a thousandth. And a thousandth would be 0.001. Yeah. Is that right? I don't know. It's about right. I know that 125 is 1/8 because my favourite fraction is 3/8, which is 375, which is the number of millilitres in a Coke can. All right. Cool. Binomial theorem. Well, I don't have very much longer, but I'll happily talk for a couple more minutes about anything. There were things on the board that is in a different lecture theatre now, so ask away anything. Oh, yes! What's the number on my shirt? I can't be bothered. I'm not going to move and stand in that exact spot. I know, I just can't be bothered. The number on my shirt is 65,536. What do you think about this number? Oh, it's 2 to the 16. Okay. And what do you know about 16? And what about 4? Which is pretty cool, but that's not why I like it. No, it's not symmetrical.
Is it a triangular number?
Not that I'm aware of. The next number is prime. This is the last power of 2 that we know of where the next number is prime. But we don't know for sure. So the only way that a power of 2 can have the next number being prime if it's 2 to the power of a power of 2. And 2 to the power of 2 to the 0 is prime, and 2 to the power of 2 to the 1 is prime, and 2 to the plus 1. And 2 to the power of 2 squared, plus 1 is prime, and 2 to the power of 2 cubed plus 1 is prime, and 2 to the power of 2 to the 4 plus 1 is prime. But none of the others after that have turned out to be prime so far. And we don't know for sure.
What's new in this course that you haven't previously covered in other...
So, yep, new in this course that we haven't previously covered. Phase diagrams were definitely new. Yeah, but we did that. I can't think of anything off the top of my head. It's been a long day. Can I borrow that for a second? Singular value decomposition is new, but that's not in the exam. Singular value decomposition is new, but as far as I'm aware, that's not in the exam. The very last thing you did in algebra.
Oh, in algebra, yeah, I'm sure it's
no, that's pretty much it. Nope. Thank you. So as far as I know, the only thing that is things that are definitely new this year are the phase diagrams and singular value decomposition. And singular value decomposition, I'm told, isn't in your exam, so we'll be fine. One day I will learn it. Everything else existed before, but in a slightly different emphasis. I might just stop there.